faithfully sharing value and interpreting great books worldwide. Hi there, this is Sally's Book Talk. Today, I'll dive into the book The Future of Humanity with the subtitle Immigrating to Mars, Interstellar Travel, Immortality, and Humanity's Destiny Beyond Earth. Earth is humanity's home, but lately, life on Earth hasn't been easy. Deadly viruses like COVID-19 and Ebola threaten our health. Natural disasters like hurricanes, floods, and earthquakes are devouring our living environment. On top of that, potential threats like supervolcano eruptions and asteroid impacts could happen too. Facing all this, we've got to ask, where should humanity's future head? If you're curious about this, why not give The Future of Humanity a listen? The author, Michio Kaku, is a Japanese-American theoretical physicist and a world-renowned popular science writer. Sally's Book Talk has covered his works like Parallel Universes and Beyond Spacetime. This book, The Future of Humanity, was published in 2018. In this book, Michio Kaku believes that facing potential disasters, humanity needs to plan ahead, think long-term, and avoid catastrophic by moving to other planets for more growth space. Our journey should be to the stars. Oh, in cosmic immigration, we'll face tons of challenges, like finding alien settlement spots, traveling through the vast universe, and surviving out there. Against these hurdles, Michio Kaku offers solutions based on solid science.
In his vision, humanity's space migration will go through 3 stages.
First, within our solar system, settling on Mars to become an interplanetary civilization. In the second stage, we'll fly to other galaxies to become an interstellar civilization. And in the third stage, humanity will challenge the universe's end by heading to parallel universes to become eternal. Now, let's follow this top physicist's perspective to explore humanity's future. Konstantin Tsiolkovsky, the father of Russian rocketry, once said, "Earth is the cradle of humanity, but one cannot remain in the cradle forever." After leaving this cradle, humanity first encounters the solar system. So, where in the solar system should we head? And how do we actually pull off this migration? That's exactly what the first section will discuss. Michio Kaku believes that within the solar system, Mars is the most suitable planet for migration. Why Mars? Because it's close enough to us. When Mars and Earth are closest, they're only 55 million kilometers apart. Of course, Venus is closer to Earth. But Venus's surface temperature can reach nearly 500 degrees Celsius. Way too hot to land on, literally burning your feet. In comparison, Mars's environment is much milder. Plus, Mars has tons of ice. Just dig a few meters underground to find it, making it relatively habitable. Mars will become humanity's first foothold in the vast universe. So the big question is, how do we actually get to Mars? With current tech, Apollo missions to the moon took just 3 days. But a one-way trip to Mars takes over 9 months. And a round trip could take 2 years. During long flights, intense space radiation and cramped living spaces severely affect physical and mental health, and prolonged weightlessness can cause osteoporosis and muscle wasting. Space sickness. Russian cosmonaut Valery Polyakov once set the world record by living in space for 437 days. But when he returned to Earth, he was extremely weak and could only crawl out of the capsule. So for migrant safety and health, we need to shorten the travel time to Mars as much as possible. That means we need more advanced rockets. A key performance metric is specific impulse. Specific impulse is the product of thrust and burn time. Higher impulse means greater total power and faster speed. Currently, most rockets use chemical engines which burn fuels like liquid hydrogen and oxygen to expel high-pressure gas and propel the rocket. So, the largest chemical engines can achieve specific impulses around 450. But this value is near the energy limit for chemical fuels. To reach Mars faster, we need engines with higher specific impulse. Michio Kaku suggests ion engines are a good choice. Ions are charged atomic fragments. Accelerate them with an electric field and expel them for thrust. These engines can achieve specific impulses up to 5,000, over 10 times higher than current chemical rockets. Unlike chemical engines that burn for minutes, ion engines can run continuously for months or even years, achieving much higher final speeds. Theoretically, ion-powered rockets could shorten the Mars trip from 9 months to just 40 days. NASA, that's the National Aeronautics and Space Administration, has researched ion engines for decades. They plan to use ion engine tech in the 2030s, just over a decade from now, to send astronauts to Mars. After arriving quickly, we'll need to figure out how to live there. Since we're aiming for migration, we can't just build small stations. We need solid plans for long-term habitation. If you've seen the 2015 movie The Martian, you'll remember how brutally tough survival on Mars is. The atmosphere is almost pure CO2, with just 1% of Earth's pressure. Lower pressure means lower boiling points for liquids. If exposed to Mars's atmosphere, human blood would start boiling.
Plus, the surface is freezing. Average temps around minus 63 degrees Celsius, so water only exists as ice.
Solving these problems is crucial for humans to thrive on Mars. Michio Kaku believes the ultimate solution is pumping greenhouse gases into Mars's atmosphere to transform its climate. This sounds sci-fi, but it's surprisingly feasible. Adding greenhouse gases kills two birds with one stone. It thickens the atmosphere so people can move around without heavy suits, just simple breathers and radiation gear. Second, the greenhouse effect would warm Mars, melting ice into liquid water. So, where do we find that much greenhouse gas? We could target Titan. Note, this moon of Saturn has abundant methane, 20 times better at trapping heat than CO2. If we ship Titan's methane to Mars via spacecraft, these greenhouse gases would capture sunlight and steadily raise Mars's temperature. Of course, Mars and Saturn are pretty far apart. We could capture nearby asteroids instead. Many contain ammonia, another potent greenhouse gas. We'd wait for asteroids to approach Mars, then use methods like nuclear blasts to alter their trajectory so they get captured by Mars's gravity. When these asteroids crash into Mars, they'll release their greenhouse gases into the atmosphere. Scientists calculated that raising Mars's temperature by just 6 degrees Celsius could start melting some ice. That melting ice would release trapped CO2, boosting the greenhouse effect even more. In other words, this creates a positive feedback loop. Mars's heating would become self-sustaining. As mentioned, Mars has vast ice reserves, especially polar ice caps. If fully melted, it'd create a planet-wide ocean over 10 meters deep. Mars warms up, liquid water forms oceans. Martian soil contains nutrients like magnesium, sodium, and potassium. With temperature, water, and nutrients covered, settlers can farm, but crop selection matters. Some biologists propose genetically engineering special algae. This algae would thrive in the cold, thin, CO2-rich atmosphere while releasing massive oxygen. With these specialized plants, we could gradually transform Mars's atmosphere. Putting it all together, the author outlines humanity's path. Master ion engines, rockets heading to Mars, then transform the climate with greenhouse gases, plant oxygen-producing flora, and ultimately remake Mars into a second Earth. Of course, this'll take centuries, maybe hundreds of years, before Mars becomes truly habitable. But it'll be worth the wait. Once Mars terraforming succeeds, we'll replicate this across other planets, creating new Earths throughout the cosmos. Settling Mars is just humanity's first cosmic step, and habitable spots in our solar system are limited. Beyond Mars, the other planets all have serious flaws. To find more planets like Mars that are suitable for habitation and terraforming, humanity must look beyond our solar system, marking the second stage of cosmic migration, journeying into deep space. In this phase, humanity faces two core challenges: finding suitable planets in the vast galaxy and traversing light-year distances to reach them. Planets don't emit light, making them nearly impossible to observe directly. So how do we detect them? Astronomers use indirect methods, most commonly the transit method, where transit means to cross in front of. Before explaining transits, recall planet-star relationships. Most planets orbit a parent star. For example, Earth's parent is the Sun. Planets don't glow, but their stars shine brightly. When a planet crosses its star, it blocks some light. Observers see periodic brightness dips. This dimming signals the star hosts planets. By analyzing these light dips, we identify stars with orbiting planets. That's the transit method. An Earth-sized planet dims a sun-like star by just 0.008%. Like spotting a mosquito passing a car headlight, but our instruments detect these faint traces. NASA's Kepler Space Telescope, a 1-ton instrument, used transits to discover thousands of exoplanets. The most famous discovered system is Proxima Centauri, the closest star to Earth after the Sun, just 4.2 light-years away. In 2016, astronomers found Proxima Centauri b orbiting it. It's 30% larger than Earth, the closest known exoplanet, and crucially, orbits within its star's habitable zone, meaning its distance avoids scorching heat or freezing cold, ideal for potential liquid water. Our Earth luckily sits in the Sun's habitable zone, so Proxima b could become another Earth.
It's clearly a potential migration target. Now we know where to go.
But how do we reach planets light-years away? Even with ion engines, reaching Proxima b might take millennia. So we'll need a much more powerful starship.
For light-year travel, Michio Kaku proposes building antimatter.
Rockets.
Antimatter is like regular matter's opposite. Electrons are negative but anti-electrons positive. Protons positive but antiprotons negative.
When antimatter collides with matter, they annihilate, releasing insane energy at 100% efficiency.
Nuclear weapons? Only 1% efficient by comparison.
Antimatter rockets work by storing antimatter, mixing it with matter for energy, achieving specific impulses of 1 to 10 million. Estimates show 9 kilograms of antimatter could accelerate a 1-ton ship to 10% light speed. With current tech, we can already produce antimatter. Back in 1995, CERN, the European Organization for Nuclear Research, created anti-hydrogen atoms. In these atoms, anti-electrons orbit antiprotons, but using antimatter for rockets faces big hurdles. First issue, tiny production. Only particle accelerators make antimatter. Current output is atomic scale, barely detectable.
As scientists say, all antimatter ever made couldn't power a light bulb. We need kilogram quantities, but accelerators cost billions, and antimatter's price is astronomical.
With current methods, 1 gram costs $70 trillion. Accumulating enough fuel for starships could bankrupt even the wealthiest nations. But optimistically, tech advances might drop antimatter's price to $5 billion per gram. Beyond production costs, storing antimatter is tricky. Contact with normal matter causes explosions. Using regular containers turns antimatter into a massive bomb. That's why we designed penning traps. Magnetic fields suspend antimatter in vacuum, preventing contact. Despite challenges, antimatter rockets offer hope for interstellar travel, reaching distant stars and even leaving our galaxy. Kaku believes at this stage, evolving from interplanetary to interstellar civilization, humanity will overcome energy and resource shortages. Asteroid impacts, supervolcanoes, even dying stars would only affect local branches of humanity. No disaster we can imagine could destroy human civilization anymore. Our only remaining enemy? Death itself. Not just individual death, but the death of the entire universe. Next, we'll explore surpassing human and cosmic lifespans to achieve true eternal civilization. Imagine traveling thousands of light years for work. Even antimatter ships would take millennia. For interstellar civilizations, such trips are routine, making extreme longevity essential. Solutions include cryogenic freezing, suspending cellular activity during travel. Cryonics companies already offer freezing services, though none can revive people yet. Whether these frozen individuals can ever be revived remains unknown. Another popular idea, cybernetic augmentation, replacing body parts to maintain function indefinitely. Of course, the most direct way is to prevent death, achieve immortality. The essence of death is the gradual aging and loss of function in the body's cells. Currently, one school of thought aims to achieve human immortality at the cellular level, and the secret to keeping cells youthful may lie in telomeres. Cells contain chromosomes that store genetic information. At the tips of chromosomes is a small complex of DNA and proteins called telomeres. Each time a cell divides, the chromosome splits too. In this process, telomeres continuously shorten. When telomeres become very short or disappear, chromosomes break down, and cells begin to age or die. To keep cells healthy, some scientists place their hopes on a substance called telomerase. Telomerase can repair and lengthen telomeres, preventing loss from cell division. Research shows that bathing specific cells in telomerase greatly increases their division count and lifespan. Although much research is still exploratory, this offers a glimmer of hope for immortality. Beyond physical immortality, there's another form called digital immortality. Simply put, it's uploading our consciousness to computers to escape bodily aging. To extract human consciousness, the US is running a project called the Brain Initiative. The human brain has 100 billion neurons, each connected to about 10,000 others. The Brain Initiative's goal is to map these neural connections, cell by cell, digitizing the entire brain. Perhaps in the 22nd century, we'll have a complete brain map containing all memories, emotions, and personalities. With this map, we can recreate our consciousness in computers and turn it into an information stream. Information can be transmitted via laser beams. Your consciousness would ride a light beam, reaching the moon in a second, Mars in minutes, and Proxima Centauri 4.2 light-years away in about 4 years. More importantly, according to relativity theory, when traveling at light speed, your own time stands still. From your perspective, this journey would be instantaneous. Once your light beam reaches its distant destination, the information gets downloaded into a robot body. Through this vessel, you could explore any planet freely. This laser consciousness transfer might be the fastest way to reach distant stars. Perhaps we'll build a massive laser highway network someday. When gazing at the stars, we'd see trillions of souls traversing galaxies, whether through cellular longevity or digitized consciousness. These advances make many believe humanity will overcome death's shadow. Yet death doesn't only claim humans. Our universe itself has a lifespan limit of tens of billions of years. How will the cosmos meet its end? Scholars propose theories. Some say the universe will gradually cool until stars fade, temperatures hit absolute zero, and all molecular motion ceases.
Another possibility. The universe contracts, stars converge, and temperatures skyrocket.
When all matter compresses together, it triggers another Big Bang, rebirthing existence.
Facing cosmic doom, must we powerless beings just wait?
Not necessarily. We might escape through parallel universes. Physicists speculate other universes beyond ours, parallel realities, likely exist. Their physical laws might mirror ours or differ completely. This concept's boundless imagination made it a sci-fi staple. In films and novels, characters enter parallel worlds to save loved ones or prevent disasters. But its true value is grander, escaping our universe's ultimate fate. Michio Kaku firmly believes parallel universes exist. The real challenge is reaching them. Enter wormholes as cosmic escape routes. Wormholes were first proposed by physicist Ludwig Flamm. In the 1930s, Einstein and Nathan Rosen refined the theory, hence the name Einstein-Rosen bridges. So what exactly are wormholes? Initially, it's seen as a narrow tunnel in space connecting 2 points. Wormholes let us teleport instantly, but some scholars view wormholes as elevators between parallel universes. Picture this. Put 2 sheets of paper parallel. Poke through both with a pencil to connect them. If those sheets represent parallel universes, the pencil hole is the wormhole. Travel through it to enter another reality. But opening wormholes isn't simple. We'd need Planck energy, the maximum possible energy for a single particle. Numerically, Planck energy equals 10 to the 27th electron volts. That's not huge, about the energy from burning 3 liters of gasoline. Here's the catch. To open wormholes, we must focus that energy onto the universe's smallest particles. Scholars believe only the Big Bang or black hole centers reach such energy densities. So, how can humanity achieve Planck energy in particles? Remember particle accelerators from our antimatter discussion? We could try using those devices. The world's largest particle accelerator sits 100 meters under Geneva. It's got a 27-kilometer circular tunnel surrounded by massive magnets. Particles get injected into vacuum-sealed tunnels. Then magnets, powered by Geneva's entire electricity output, accelerate them. Yet this colossal machine only achieves 100 trillionth of Planck energy, barely a fraction. Clearly, we're nowhere close. If civilization advances enough, we might build a solar system-sized particle accelerator in space. Space vacuum beats Earth's best vacuums. So no tunnels needed, just magnetic stations along a looped path to steer particle beams. Imagine particles in a cosmic relay race. Each magnetic station gives them a speed boost until they reach Planck energy. Focusing this energy at one point could open a wormhole to parallel universes. That means we'd have the key to parallel universes. Though keys alone aren't enough, scholars still need to solve critical issues, like how to stabilize wormholes and ensure they lead to suitable universes, etc. But for now, we can boldly imagine entering a young new universe as our home through wormholes. In this new universe, atoms would exist stably, and stars could form new planetary systems. If achieved, our universe's death wouldn't be the end, just the start of a brand new story. Now, shifting focus from parallel universes, let's revisit Michio Kaku's vision for humanity. A core theme in humanity's cosmic evolution is accessing ever greater energy sources. From chemical rockets to ion engines, antimatter to Planck energy, more energy lets us reach farther. From solar system to galaxy, cosmic edge to parallel universes, humanity's civilization spans planets, then galaxies, achieving eternity, an unimaginably grand vision. You've noticed we used terms like possibly and maybe. Much content is speculation based on current science. Scientific theories constantly evolve. Today's certainties may be revised tomorrow, so our future interpretations remain fluid. But isn't the future's true charm its unknown, uncertain nature? All right, that concludes our interpretation of the future of humanity. Reading notes are below the audio. See you next time.